Hi, everybody. My name is Ugur. I'm a research associate at Alan Turing Institute. Thanks a lot for the opportunity. It is great to talk in this platform. And today we will talk about private and secure fuzzy name matching, and my colleague Harsh.
Hello everyone, I am Hers, working as a research associate in Alan Turing London. My research interests are private data sharing and privacy preserving machine learning, and I will be talking with Ugar on this private and secure fuzzy name matching. Ugar, please.
Thank you. So, yeah. So the first part of the talk be covered by me, and then second part I will hand over to Harsh. If there is any connectivity issue, please feel free to interrupt us because we face several issues today. Yeah. So we both are research associated at Alan Turing Institute and working in the research group of Professor Carsten Maple. And in our research, we don't only look at how we improve the existing tools for privacy preserving computation, but we also look at how we can improve the practicality, how we can implement into real world use cases as well. So in this manner, we can say we do more privacy engineering. And the areas we are mainly implementing focusing is finance, digital identity, and healthcare. Yeah, and if we look at what are the available tools are in the literature, we can say the most basic tools are anonymization, and there are tools like cryptographic approaches for like FHE and second mode part computation. There are tools based on data perturbation like differential privacy. We can consider access control and data minimization based on tools as well for introducing privacy. Obviously, among these, anonymization tools has been broken so many times, and the main challenge of the anonymization is like we cannot assume how much background information an adversary can achieve. So it is not really possible to provide privacy by only anonymizing data. On the right side, there are several famous examples how anonymization has failed. So that's why our research is looking more on the other approaches like FHE. And if you look at what are the challenges for achieving privacy preserving data sharing, we should understand what are the risks. So for that, we look at the threat model of the system. So what are the threat model of the parties collaborating? Is it semi-honest or is malicious? What can go wrong in the system? And if we apply tools like FHE, is there an accuracy drop? In FHE setting, accuracy drop can be, there might be some minimal accuracy, but is this accuracy important for our system, or that is negligible accuracy loss? On what is the timeliness of the computation? What is the trust relationship between the parties? In our today's use case, we consider collaborating finance. We can consider they are trusting each other to a certain degree. And what is the scale? So how many parties are collaborating? And what is the existing tools? What is the existing regulations that we should consider? Yeah, and the governance of the scheme. And if we go more deeper into finance, private data sharing is required for several use cases of finance. These include identity sharing, like today's talk for fuzzy name matching. This is important in several topics, including fraud detection and money laundering. Because we can consider there are anti-money laundering system and fraud detection system in multiple banks, and they can identify suspicion activities, but to investigate in these activities, it will take time, and it will take time, and it will take cost for the banks then. But if they can share about which suspicion activities they identified, maybe they can prioritize these activities more, and that will give advantage to them in terms of time. Yeah. And in terms of finance, there are several limitations we should consider. So financial data is highly sensitive, and it is usually kept in private, so we cannot probably achieve a lot of training data. And fraud detection data is not very rich, because frauds are not happening frequently. They are very skewed, and the domain has strong privacy and security concerns. That's why movement of the data is highly restricted. And based on this consideration, we can develop our solution. Yeah. This study has been done by Harsh, me, Professor Karsten Maple, Professor Graham Cormode, and Jing Conhe. The study is in collaboration with HSBC, and we try to solve one of the real life problems in finance. This is for achieving privacy preserving fuzzy name matching for cross-border data sharing. Yeah. And okay, so there are international banks operate in multiple countries, and each country they have their anti-money laundering systems, and when they see suspicious events, they report to their financial intelligence units, and then the investigation goes on. Although it is the one entity internationally, they cannot share the findings of their own algorithms among them. It should go through the process like reporting to the financial intelligence unit, and it will take time. And if we consider the number of frauds are increasing, there were statistics in the last considering the last 6 months of the statistic, frauds are increased 15% in the UK, which is like over 200,000 attempts. And so we should be more timely, and we should prioritize real fraud attempts more. So our use case aim to share the knowledge, so the banks will know which suspicious entry identified in the other party as well, that they can prioritize the investigation for that party. Yeah. So our threat model considers semi-honest threat model, because in these organizations are part of the same entity, and they will not manipulate the existing scheme, and they will not try to achieve further. So yeah, so they follow semi-honest threat model. And so if we consider to finding similar names, the first thing can be how these names are similar in terms of added similarity. So based on the differences in the characters, how much these names are similar to each other. But that will be not very applicable in the FHE settings, and because it might require the checking character by character. That might be costly. So we need another solution. That's why we looked at more statistical similarity. So if we convert names into a vector, how much these vectors are similar to each other? That will give us more rigorous solution. And we chose cosine similarity because it does not change based on the length of the vector, and it gives us opportunities in computation in encrypted settings. Yeah. And to produce the signatures of the names, we looked at local sensitive hashing methods. So one of these methods is min hash algorithm. So compared to the general hashing methods, local sensitive hashing methods aims to give same hash value to give similar hash values to similar items. So we can generate a set of hash values that will give features of the name. And for that, we cut the name into smaller parts, such as like 3 grams of the name, like every 3 letter. And then we hash these letters based on an hashing method, and then we applied min hashing algorithm. Yeah. For the following part of the talk, I will hand over to Kasyap. Thank you so much.
Yeah. Hello, everyone. So now I will go through the scheme that we developed. So here there are two organizations, A and B. A is the courier and B is the responder. And they have their own private data set. They generate the signatures using the min hash scheme. We can see in the first box, in the top box, they encrypt the plaintext query using fully homomorphic encryption, and they send it to the organization B. So organization B received the encrypted queries and try to compare it with the plaintext. So the B is not doing encryption. B has plaintext and A has encrypted queries, and it performs encrypted evaluation, and these results are sent back. So this looks very simple, right? And the results are decrypted at the courier's end, but this has flaws that first it will take too much of computation cost to create the similarity with million names. Suppose that organization B has 10 to the power 6 or 10 to the power 7 names. So it will take 1 to 10 to the power 6 computation in encrypted domain, and returning all the results will allow organization A to infer the presence or absence of some of the names at the organization B. So this is a very nice solution to search a query at the side of the responder or the other organizations, but it needs to be enhanced from both communication perspective, computation perspective, and privacy perspective. So we propose a clustering based solution which reduces the cost from perspective of computation, communication, and also from the enhances the privacy. How? So as discussed, that the responding party may have a huge list of names, right? So the organization B, the responding organization, can do a clustering at its own side based on the similar names, and it prepares. Let's assume that the organization B prepares a root D cross root D square matrix for given D names. However, it is not possible that to get a square matrix because we cannot fix the number of names in a particular cluster, right? Because it may be that, for example, names in the distribution may not be uniform, it may be non-uniform. So in that case, the cluster will be padded to have the same length. Then organization A encrypts the encoded name, the name to query and sends to B to match with the centroids of that particular square matrix that you are seeing here. So in this case, and B will not be able to learn that from which centroid it is matching, because the result will still be encrypted. Then B calculates dot product with the encrypted query with all the centroids. So dot product between the normalized vectors gives cosine similarity, and we discussed that we are using cosine similarity because of its independence over the length of names, like uh, for example, Mary Jones and Mary Jones appended with some Mary Jones and appended with some other surname, a third name. So A is the querying party and B is the responding party. So suppose B has D names and D is in the order of 10 to the power 6, 10 to the power 7. So B will do clustering at its end. So assume that B is able to create a root D cross root D square matrix. However, it is not possible because it is not possible to have each cluster of same size. The distribution of name will not be uniform. In that case, same size. In the second step, organization A, the querying organization, encrypts its query and sends to B to match only with the centroids, not with the whole set. So B calculates the dot product between the encrypted query with all the centroids. So we can assume that the centroids represents the first column of this square matrix. So, and dot product between normalized vectors returns the cosine similarity. Now organization B sends the cosine similarity scores to A, which is encrypted and not learned by B. Then A can decrypt the vector, and decrypting it can learn that to which centroid it is matching the most. So A learned nothing but the cosine similarity scores between 0 to 1. A has not learned that which position or which particular centroid or encoded value it has matched with. So suppose there are root D clusters, then A learns root D cosine similarity scores. So for 10 to the power 6 names, A received 10 to the power 3 scores, which is like 1000 cosine similarity scores, which will not reveal anything, but it will only tell that to this particular row, there is high chance to get a potential match. Okay, so organization B sends the cosine similarity scores compared with all the centroids to the courier party, and the courier party received root D scores. So suppose given a data set of 10 to the power 6 names, the clusters were approx 10 to the power 3, like around 1000 clusters for let's assume 1000 clusters. So A receives, we reduced the communication from 10 to the power 6 to only 10 to the power 3 for the first round. So A received 10 to the power 3 cosine similarity scores. And based on that scores, A prepares an indicator vector or a sign vector, which and assigns and score 1 to the particular centroid where there is a chance of potential match. There is no guarantee that there is a match there, but there is a chance of a potential match there. And assigns a score 0 to rest of all the centroids. So A prepares a sign vector of size root D, where one value is 1 and all the other values are 0. Then A sends the encrypted sign vector to B. So, and in the next step, we can visualize it like this. Like this, this is a sign vector which has one value of 1 and the remaining are 0, and it is multiplied with one column at a time. So for example, given 10 to the power 6 names, suppose we have, let's assume the ideal case that we have 10 to the power 3 cross 10 to the power 3 square matrix, 1000 cross 1000 square matrix. Then at one time, the sign vector will be multiplied with one column, and it can be parallelized based on the computational strength. Like so what to visualize that the sign vector is multiplied with one column, which will result into one encrypted name at the responding party, right? So we can see that NB13 represents a name in the potential matching row or the potential matching cluster from where there is a chance that A feels that a name could, a similar name would be present there. And this operation can be parallelized. So this was the main main proposal which is reducing the cost, and at the same time we don't need to wait till the end of the cluster to receive the match. Yeah. And now since B has found the potential location to calculate the cosine similarity with, so in the next step B finds the dot product between the output from the previous step to the original encrypted query. Now again, we have reduced the computation issue and communication issue, but if A returns the exact score back to B returns the exact score to A, the problem of privacy remains that B is returning all the cosine similarities in the potential matching cluster that may help A to query some inference attacks and to learn the presence or absence of a particular name held with B. So because the problem, we defined the problem like we have to find that there is a match or not match. There is a chance of potential match or not match, 0 or 1. We are not supposed to reveal the score back to A, right? So what we do, that organization B subtracts the threshold from the encrypted cosine similarity value. Like suppose organization B calculated the encrypted cosine similarity in the previous step was encryption of 0.9, and we have the problem or the organization have defined the threshold of 0.85 for a possible fuzzy name matching. So organization B will subtract 0.85 from encrypted 0.9, which will result in encrypted 0.05, right? And it will multiply with any positive random number, any random number in ZP prime. So if there is a match, that there will be an encrypted positive number, or if there is not a match, there will be an encrypted negative number, and that will be random. So anything encrypted positive number, it represents a match, and any encrypted negative number represents a non-match. So which addresses the privacy issues in the NAP solution that we had discussed first. Now the organization A receives the encrypted score and decrypts it with its own secret key. If the score is positive, then it can be considered as a potential approximate match present with B. It doesn't tell anything else that how close it was or how closely it was matching or not. It just tells a match or non-match. So it fulfills the requirement of privacy. It reduces the communication cost by huge, as well as the computation cost. We will briefly discuss the results. Since we used MinHash for encoding the names, so we tried with different sizes like 50, 100, and 200. Of course, it is directly proportional to the size of encoding length, the cost, right? So what we did that for clustering, because clustering was more sensitive, for clustering we used the encoding length of 200, and after clustering, when we are operating on a single potential matching row or potential matching cluster, we fall back to encoding length of 50. So for the first round, to get the potential matching cluster, we use a high encoding length, and then we fall back to encoding length of 50. Okay. And we tested our results on different data sizes from 10,000, 100,000, and 1,000, 10 to the power 6. And if you are not using any clustering, then the total communication involved was exactly 3.14 GB, given 100 queries to 100,000 at the responding party. And when we use clustering, even in the worst case scenario, the total communication involved was 53 MB, 53.9 MB. And even we reduced the memory consumption for this. However, now we represent how clustering worked and why the worst case scenario and the best case scenario of clustering. So let's see the figure C for 100,000 names. If we cluster into 50 cluster, 100 cluster, 500 or 1,000, we can see that more than half of the names are covered only in 1 cross 10 to the power 4. Like the x-axis is representing 0 10 to the power 4, 1 cross 10 to the power 4, and the y-axis is 10 to the power 6. So we can see that only few clusters are very long. Most of the clusters are finished. I have noted on the number, like the maximum number of columns with 50 clusters is 4206. More than 50% of names are covered only in 1000 columns, 80% in 2000 columns, and 90% in 2500 columns. So the time taken to compute on each column in the given settings is 0.26 seconds. So it would take a maximum of 260 seconds to search from 50,000 names, 520 seconds from 80,000 names, and 650 seconds from 90,000 names. So it improves the search time by a lot from the serial, sending back the result linearly or serially. Since we used CKKs for this, or even many FHE schemes support batching. So increasing the number of queries from 1 to 10 or 100 to or 1000 doesn't impact the performance. It only impacts the cost in the first round for matching with the centroids. So we can see that if we have 10 queries, it takes 1.4 seconds in first round, and if you have 1000 queries, it takes 1.98 in the first round. But the time to operate over each column remains same even after increasing the number of queries. But increasing the number of queries or batching also has a limitation that we can batch up to certain queries, specifically in the algorithm that we used. So but it doesn't impact the per column computation cost and neither the communication costs. So and this satisfied the requirement of unbalanced fuzzy name matching. Yeah, thank you, and we are very sorry for the interruptions in between, and now we are open for questions.